Welcome to the next chapter. It's reaction rates and reversible reactions. Now, chemical reactions occur and proceed at different speeds, and whereas some reactions may take a very short time to occur, others take a considerable length of time, but still some occur at moderate speeds. Now, during chemical reactions, the reactants are converted to products. In what we call unimolecular reactions, one reactant is converted to one product. For example, A, the reactant, is converted to B, the product. Now, in other types of reactions, we call bimolecular reactions. Two reactants combine to give either one or more products. For example, A plus B would give us C, or A plus B could give us C plus D. Now, we could also have trimolecular reactions where three reactants combine to give one or more products. Now, the rate of a reaction can be measured by the rate of disappearance or consumption of the reactants, or by measuring the rate of formation of the product. Now, these changes may be seen either as change in color or measuring the volume of a gas produced at certain time intervals. But basically, the bottom line is that the property to be measured should vary with time while the others remain constant. And how is this important? Well, the knowledge on the rates of reactions is important in understanding how fast products in an industrial process can be obtained in a cost-effective manner. How? By giving the best conditions for the production. But before we look at the factors affecting the rates of the chemical reactions, let us look first at something that we call collision theory and activation energy. Now, chemical reactions involve collisions of the reacting species. However, for a reaction to occur, certain conditions must be met. First of all, the particles must collide in proper orientation, and secondly, the particles must possess a certain minimum amount of energy that we call the activation energy. This way, we say the collisions are successful. So not all collisions result in chemical reactions. As a matter of fact, most collisions that occur in nature are usually unsuccessful. Successful collisions are very rare in nature. Why? Because either the collisions are in improper orientation or the particles do not have enough activation energy. Now, to properly understand what activation energy is, for instance, let us say I want to roll this ball up the path. Now, if I don't give it enough push, it will roll up and then come back to where it was. But if I give it a better push, it will roll up and then all the way down to the other side. So you see the ball had certain amount of energy here at the beginning. Now it has lost some of it eventually when I got it to the other side. But those are not the only two energies, because you see I had to put in some energy first to set the ball in motion. Now this is what we call activation energy. Now this is what usually happens in chemical reactions. You can think of this point as the reactant and this as the product. And although we only consider the energy change between the product and the reactant, you will appreciate also that some amount of energy was needed to kickstart the process. Now in this case, the energy change was negative, and this is an exothermic reaction. Now if I consider an endothermic process that requires energy, I'm going to put in more energy and I'm going to get some of that back, and everything else is the activation energy. For instance, if methane and oxygen are put together, the molecules will collide, but they lack the activation energy to react. Now a flame can provide this activation energy, and the bonds break and new ones form in an exothermic reaction. So in an energy level diagram, initially the molecules collide, but they lack the activation energy. A flame provides this activation energy, and the bonds break and new ones form in an exothermic reaction that releases energy. Now the energy released supplies the activation energy to other molecules and the mixture explodes. Again, nitrogen and oxygen exist in the atmosphere, colliding but never reacting. Why? Because they lack the activation energy. Now, heat from lightning supplies the energy to break the bonds, and new bonds are formed in an endothermic reaction that absorbs energy. Reactions that require very little activation energy occur spontaneously. For instance, when phosphorus is exposed to air, it smolders spontaneously in a reaction with oxygen. Other reactions require large amounts of activation energy and therefore do not occur spontaneously. In exothermic reactions, once the activation energy is sufficient, the energy evolved in the reaction supplies the activation energy for the other particles to react. For example, a mixture of iron and sulfur does not react, but when a red hot rod is placed in the mixture, it supplies the activation energy. Now the exothermic reaction continues. Why? Because the energy generated in the exothermic process supplies the activation energy and the reaction drives itself. Now, generally, a successful collision occurs when the particles collide in proper orientation and possess sufficient amount of energy to kickstart the process. Now, the minimum amount of this energy is what we call the activation energy. Now, so much for that. Let's go back to factors affecting rate of reactions. Now, there are several factors that affect the rate of reactions, and they include temperature, surface area, catalyst, light, concentration, and so forth. So we look at them in details one after the other, and we start with temperature. Now, usually an increase in temperature leads to an increased rate of a chemical reaction. For example, if I react a metal with an acid, I get salt and hydrogen according to this equation. Now, if I set my experiment so that I measure the volume of the gas produced at certain time intervals and then draw a curve for that data, I shall have a curve of this nature. Now, from this curve, the maximum volume I get is 60 centimeters cubed. That's an arbitrary value that I've picked. Now, if I raise the temperature of the mixture and repeat the procedure, I will have a curve of this nature. Now, you realize that the two curves flatten at the same volume. Why? Because I have fixed amount of reactant. The volume of the gas produced does not change. The only thing is that I will take less time to get the volume of 60 centimeters cubed at high temperature. Now, if I lower the temperature, the curve will be like this, and again the maximum volume is the same. The only thing is that it takes longer to get there at low temperatures. Now, when temperature is high, the heat increases the kinetic energy of particles, so they move faster and thus increase the number of collisions per unit time. So overall, reactions proceed faster at higher temperatures. Next is concentration. Now, when the concentration of one or both of the reacting species increases, the rate of the reaction also increases. Now, that information can be represented by the following curves. Now, however, the situation is quite different if you increase the concentration of only one of the species. If you increase the concentration of one of the species, the maximum volume is constant. However, if the concentration of both of them is increased, the maximum volume also increases. You need to take a look at the curve on the right side of your screen. You realize it's quite different from that on the left. Increasing concentration means increasing the number of particles and thus increasing the rate of collision of these particles, and hence the rate of reaction also gets faster. Next, we have a catalyst. Now, when hydrogen peroxide is left on its own, it slowly decomposes into water and oxygen gas according to this equation. However, this process is slow and the amount of gas produced at a given time interval is also very small. However, when manganese 4 oxide is added, the decomposition is quite fast and a large amount of oxygen gas is generated within a short time interval. Now the graph for this will appear as shown here, and again the final volume is the same. What differs is the rate of that reaction, the amount of time taken to obtain that maximum volume of the gas. Another interesting thing to note is that manganese 4 oxide remains chemically unchanged in the end of that process. It only speeds up the rate of reaction. Such substances, we call them catalysts. Now, most catalysts act by providing surface area on which particles can react. Some act by forming short-lived intermediates which will then break up to give the product and the catalyst. So it is not exactly correct to say that a catalyst does not participate in the reaction. It just remains unchanged in the end. A catalyst provides an easier route for the reactants to attain the minimum energy required for the reaction to take place. So therefore, catalysts actually lower the activation energy. So we can have this kind of an illustration. You realize the production of oxygen gas is faster when you use a catalyst, but eventually the volume of the gas produced is the same. Now it's important to note that a particular catalyst will accelerate a particular reaction, but not all reactions. Now energies of the reactants and products remain the same, only the activation energy is lowered. The next factor is surface area. Suppose I reacted a marble chip, that is calcium carbonate, with hydrochloric acid. Now you realize in this experiment a stream of bubbles is seen as carbon dioxide is generated. Now, however, if I take the same marble and ground it into fine powder and again react it with hydrochloric acid, this time you realize the reaction is now more vivid as effervescence is seen. Now, in other words, the rate of a reaction is faster in the ground calcium carbonate. However, the amount of carbon dioxide produced will still remain the same. Why? Because the size of the marble is fixed. Powdered calcium carbonate has a larger surface area than the marble chip, and the graph for this experiment would appear as shown on your screen. Next, light. Now light is also a form of energy and affects the rates of some reactions. For instance, when chloric 1 acid is left in the dark, nothing would happen. But in the presence of UV, the acid decomposes according to this equation. Now the other reactions that are also light dependent and include: 1. The reaction of hydrogen and chlorine, which react explosively when exposed to light according to this equation. Halogenation of alkanes, for example, bromination of methane, requires the presence of UV to form bromomethane and hydrogen bromide. Photosynthesis, the process by which plants make their own food, is also light dependent. That's why plants do not manufacture food at night. They need sunlight. Next is pressure. Now, pressure affects reactions involving gases only. Pressure is caused by collision of gas molecules with the walls of the container or vessel in which it is contained. Now, when pressure is increased, it causes similar effects as increased concentration. Mostly increased pressure is accompanied by decreased volume, and thus the molecules interact more and are closer together and also travel shorter distances. Increase in pressure increases the rate of reactions involving gases. Now liquids and solid are not affected by pressure. Why? Because they are not compressed. Now, having considered all these factors, let us look at the general rate of a reaction. Now, we have indicated that the rate of a reaction can be measured by one, measuring the amount of a gas produced if the reaction does so at certain time intervals. Now, if you do that, we often obtain a curve of this nature. Now, a clear look at this curve will tell you that the rate of a reaction is fast initially. You realize a large volume of gas is produced within a very short time interval. But again, this process slows down with time. As time goes on, you realize the rate of reaction goes down as well. So why is this the case? Now, one of the factors that affect the rate of a reaction is concentration of the reactant. Now, when the reactants are in very high concentration, the rate of reaction is very high. Why? Because the number of molecules or particles that are colliding is quite high, and it increases the chances of having successful collisions. But you realize as more and more reactants are being converted to products, the concentration of the reactant is going down. So the rate of reaction is bound to go down. So the explanation for this nature of a curve is that as the reaction proceeds, the reactants are converted to products, and therefore the concentration goes down, and thus slowing down the rate of a reaction. Now, after that, we look at reversible reactions. Now, when a reaction occurs, the reactants are converted to products. We've said that over and over. Now, in some reactions, the product formed can be converted back into the reactants. For instance, if we heat ice, it melts into liquid water. We can reform the ice by reversing the process, that is, by cooling the liquid water. Now, in other reactions, the product formed can never be converted back into reactants. For example, if you burn a paper into ash, the ash can never be used to reform the paper. Again, if you burn methane to give carbon dioxide and water, we cannot reform methane from water and carbon dioxide. Reactions that go on in either direction are called reversible reactions. For instance, if we heat blue hydrated copper 2 sulfate, it loses the water of crystallization to form white anhydrous copper 2 sulfate. When water is added to the white anhydrous copper 2 sulfate, the blue salt is reformed again. Now, these reactions could be represented as shown here. Copper 2 sulfate, the hydrated salt, when heated, it loses the water of crystallization to form anhydrous copper 2 sulfate, which was white in color, plus the water. Now, the left to right reaction is called the forward reactions, and the right to left reaction is called the backward reaction. Now, we can also have the following reaction. Cobalt 2 chloride, when heated, it loses its water of crystallization to form anhydrous cobalt 2 chloride. Hydrated cobalt 2 chloride, when heated, it loses its water of crystallization to form anhydrous cobalt 2 chloride. Hydrated cobalt 2 chloride is pink in color. The unhydrated salt is blue in color. Again, when water is added, the hydrated salt reforms. So that brings us to what we call equilibrium. Now, both the forward and backward reactions can occur at the same time depending on the conditions under which the reactions occur. For instance, if we have white fumes of ammonium chloride in a closed system, remember ammonium chloride decomposes to ammonia and hydrogen chloride gas. And again, ammonia and hydrogen chloride can combine to give ammonium chloride. Now, if the system is heated, both the forward and backward reactions do occur. Now at first only the ammonium chloride is present, and thus its concentration is quite high. On warming, it decomposes into ammonia and hydrogen chloride. Now initially the forward reaction is faster. Why? Due to the high concentration of ammonium chloride. Now but with time the ammonia and hydrogen chloride build up and the backward reaction takes place. Now this continues for a while until at a point where the rate of forward reaction equals that of backward reaction. There is a state of balance and the system appears not to be changing. This is the state of equilibrium, and it is represented by the double half arrows as shown next on this equation. Now remember that at equilibrium both forward and backward reactions still take place, albeit at equal rates, and this is called a dynamic equilibrium. Now the state of equilibrium is of course affected by several factors, depending again on the nature of the reacting species, whether they are gases, liquids or solids. Now let's look at the factors affecting equilibrium, and I've said the state of balance or equilibrium of reversible reaction can be changed by altering environmental factors such as temperature, pressure and concentration. Now let's start with concentration. When the concentration of one or more of the species is increased, the system shifts as to favor the consumption of that species. For instance, in this system of ammonium chloride decomposing into ammonia and hydrogen chloride, if we inject more ammonia into the system, it will respond by producing more ammonium chloride and thus consuming the ammonia that we have added. Now the backward reaction is therefore favored. Now the same will happen if we increase the concentration or the amount of hydrogen chloride. So we say equilibrium shifts to the left. Where the equilibrium shifts, that side, the product on that side are produced more. If we however increase ammonium chloride, the equilibrium will shift to the right and more ammonia and hydrogen chloride will be formed. Now this behavior of systems in equilibrium is governed by the Le Chatelier's principle, which states that when a change in condition is applied to a system in equilibrium, the system moves so as to oppose the change. So when we increase the amount of ammonia, the system will oppose. How? By producing more ammonium chloride, thus reducing the amount of ammonia to re-establish the equilibrium. The next factor that would affect equilibrium is pressure. Now pressure only affects a system involving gases. We said pressure is caused by collision of gas particles with the walls of the reaction vessel. Now the more the number of molecules present, the more the collisions, and thus the higher the pressure. Now in simple language, if the pressure is increased in a system in equilibrium, the system will favor the direction that produces less molecules. For example, nitrogen 4 oxide and dinitrogen 4 oxide can exist in equilibrium. Nitrogen 4 oxide and dinitrogen tetraoxide can exist in equilibrium as shown on this equation. On the left side we have 2 molecules and on the right we have 1 molecule. Increase in pressure will favor the production of dinitrogen tetraoxide since it has less molecules. Now thus equilibrium will shift to the right. Now this can be demonstrated if a mixture of these 2 gases is contained in a closed system. Now the gases exist first at equilibrium. Now when I compress the system, the mixture turns pale yellow due to formation of dinitrogen tetraoxide. Again, when I release the pressure, the mixture turns dark brown, meaning the dominant gas there is nitrogen 4 oxide. If the number of molecules is the same, change in pressure does not affect equilibrium. For example, a reaction between iodine and hydrogen gases to produce hydrogen iodide gas. There are 2 molecules on either side, so change in pressure won't affect the state of equilibrium. And then we have temperature. Temperature also affects the equilibrium. Now, for a system in equilibrium, increase in temperature will favor the endothermic process. That is where the enthalpy change is a positive. Decrease in temperature will favor an exothermic process where the enthalpy change is negative. For example, if I have a system P plus Q to give me R plus S and the delta H is negative, that means it is an exothermic reaction. The forward direction is exothermic and the backward is obviously endothermic. Increase in temperature will shift the equilibrium to the left to favor the endothermic process. Next we have catalyst. Now catalysts don't have any effect on the state of equilibrium. It only speeds up the attainment of equilibrium. Now finally we look at some industrial applications of chemical equilibrium. And the first process is the Haber process. Now the Haber process is the large-scale manufacture of ammonia. How? By combining of nitrogen and hydrogen gases. Now the reaction is shown by the following equation. Now how does environmental factors affect this equilibrium? Let's start with temperature. Now the synthesis of ammonia is an exothermic process. The delta H is negative, enthalpy change is negative. Now high temperature will not favor the forward process. Now to yield more ammonia we need to lower the temperature. However, the rate of production will again go slow because initially we said increase in temperature increases the rate of a reaction. So we need to strike a balance to get an optimum temperature, and the optimum temperature used in Haber process is about 450 degrees Celsius. Pressure, again you realize the product and the reactants are gases, so pressure has an effect. Increase in pressure will favor the forward process. Why? Because in the forward process we have fewer molecules, 2 compared to 4 on the reactants. Thus at high pressure the yield of ammonia is high, but the cost of producing high pressure and maintaining it is enormous. An optimum pressure of 200 atmospheres is normally applied. Next is concentration. We also said that concentration affects the equilibrium. Now if the process is allowed to go on unchecked, the equilibrium will be attained and nothing will go on. So usually the ammonia that is formed is continuously removed to lower its concentration and hence favoring the forward reaction that converts or combines nitrogen and hydrogen to yield more and more ammonia. Catalyst. The catalyst used is iron. Platinum would be a better catalyst, but it is expensive and easily poisoned by impurities. The next industrial process is the contact process, and this is the manufacture of sulfuric acid. Now there is this stage where sulfur dioxide or sulfur 4 oxide and oxygen combine to yield sulfur 6 oxide. The equation again is shown here in equilibrium. How does temperature affect that? Now you realize increase in temperature will favor the rate of reaction, but again will favor the backward reaction since the forward is an exothermic process. Now for maximum yield, an optimum temperature of 450 degrees Celsius is used. Pressure, all the materials there, all the products and reactants are gases, so pressure has an effect. High pressure will favor the forward reaction, so optimum pressure used is the atmospheric pressure, giving a conversion of sulfur dioxide to sulfur trioxide of 90%. Finally, the catalyst used is the vanadium 5 oxide. Vanadium 5 oxide is used as a catalyst to speed up the process. Remember, the catalyst does not affect the state of equilibrium, it only speeds up the attainment of that equilibrium. Now that's pretty much for reaction rates and reversible reactions. Now let's get a summary of what we have learned.
The Royal Institution in England had very quickly, in the early 1800s, devised a very large bank of batteries. In fact, the batteries consisted of 2,000 cells. If these cells produced each about 0.7 of a volt, you can imagine even 2,000 of those connected in series would have given quite a large amount of electric current. Michael Faraday started experimenting with this new form of energy. And it wasn't long, as one can imagine, before all sorts of discoveries were made. Ørsted realized very quickly that if an electric current was passed through a wire, that a magnetic field could be generated. Michael Faraday realized that if you took one piece of wire and you laid it parallel with another, passing current through one of the wires induced, by not physical connection but by electromagnetic connection, induced a voltage in the wire lying parallel to the first one.